Alright, so today I'm going to be explaining this important paper with the title Discrete Flow Matching. This paper in 2024 by Meta AI. Despite flow matching and diffusion models have emerged as powerful generative paradigms for continuous variables such as images and videos, for graphs and language or anything discrete data like tabular data, it is limited. So we present a discrete flow matching, which can be used for generating discrete data. So the contributions is that it works with a general family of probability path interpolating between source and target distributions. It allows for generic formula for sampling from these probability paths using learned posteriors such as probability denoiser and noise prediction, and focusing on specific probability path defined with different schedulers improve generative perplexity. So they did it for code generation examples, for code generation, and also other examples. So their notation is very, I've seen this notation in many papers. So we use P of X to say that it's a PMF because we are working with discrete data. We have mass function, and to describe marginalization, we use this script, X sub I. For example, the ice token, the ice position. It's about position. For example, when you want to generate a sentence, there is an ice position. And there is this, so this is the marginal one. And in the discrete generative models, our goal is to transform source samples. So we want to move from this distribution P to our target distribution Q. So we are adding a special token value which uses mask or dummy token, which we say is a M. It means mask. And so any random sample that realizes this choice is a random sample from the training data. The second choice of coupling between the source and the target distribution, the source and the target sample, which we find improves conditional sampling, partially masks input. So this is just the entry-wise product. So we call this C coupling. It's conditional coupling. So this is one formulation of this discrete score matching. Another formulation that I found more interesting was Campbell. Campbell is a very good researcher in MIT. His notations are very beautiful, very clean, very disciplined. So his papers are very easy to follow, their notation, everything. And again, it's the similar idea. We want to use this continuous Markov chain, continuous time Markov chains, in that we have time. I mean, time at any time you can sample. It's not just discrete time that you only have finite discrete times. Here, at any time you can sample, and we can use it using the rate matrix in continuous time Markov chain theory. We can easily go from one state, for example, in nodes or edges of a graph, or when you want to change the word, flip the word in language modeling, you go to another category, then another, you stay there for a time, then you go to another, you stay there for a time. And these times when you model this using the rate function and the reverse rate function, you can learn, and the learning can be either using elbow, as Campbell has used the continuous version of elbow, or different losses. You don't need to just use elbow as an approximation. But the idea of continuous time Markov chain is very interesting for many reasons. For defining flow matching in discrete setting, we follow this paper, again by Campbell. So x sub t is just the jumping between states in your dictionary, and in your data, and depending on continuous time value. So similar to continuous flow matching, we focus on a model that predicts rate of probability change of the current sample. So each token of the sample is updated independently. This U, we call it probability velocity, which is reminiscent of velocity field in continuous flow matching. So this U is, and this is we have generating velocity field. Probability velocity generates the probability path, and given a sample, the sample satisfies this. You can approximate this. There is an order of h which you are ignoring. And then you have this interesting theorem that given a conditional probability velocity, the marginal velocity is defined by this. It generates the marginal probability by the Bayes rule. So for continuous continuity equation, of course, is the general one is the Fokker-Planck, but Fokker-Planck instead of 0 have some noise as well, but we ignore it because we assume we are doing flow matching, so we are ignoring the noise. That's why it becomes the continuity equation rather than Fokker-Planck. And then if you want to do it for discrete data, you need to, instead of divergence, now it becomes this. Your divergence becomes this, because z is, when you want to flip, then the distance between z and x and z, it becomes an equivalent of divergence, because now we are working on discrete data. And then if you follow this, so we wrote the divergence like this, and a direct calculation shows that you can relate it to u and ptz. So this table shows everything. For discrete flow matching, you have this probability of xi condition on source and target sample that looks discrete, because you have your elements, each xi is a discrete variable. For continuous flow matching, it's like, of course, in stochastic interpolant, there is a theory, a physicist, a cosmologist defined this x0, let's say x0 xt, for example, any source and any target at any time, you can define it as, for example, tx1 minus t xt. But the difference between this and flow matching is that you are sampling even the x of s and x of t, you're sampling it. So it's a distribution. But still it's deterministic. That's why they add another term to model the noise. So this is an interesting research area which is a generalization of flow matching and diffusion, and also Schrödinger bridge, which is interesting because it unifies all of these theorems. Also, if you go from continuous to discrete, it's interesting to look at that. It's universal. A generating probability velocity for the path is this. So this is the probability denoiser. Of course, the paper of Campbell is much easier to follow, and their notations are much more interesting. But this paper is somehow equivalent to those papers of Campbell. But for training here, they use this loss. You know, equation 22 is marginal probability velocity. If you apply it to conditional probability, it gives this. And now here, equation 22 shows that generating samples from probability path, we require the posteriors omega hat, W hat. And training such posteriors can be done by minimizing this loss. So they did experiments on different data sets. They even compare autoregressive with flow matching, both for text generation and code generation.